Hey everyone, in this video we're going to be going over the Physics 103 Discussion 3A Useful Expressions. Starting with the top left function, let's say I have a soccer ball and I kick it at a 30-degree angle in respect to the horizontal, and it has a velocity of 5 meters per second. So I'll just go and fill the x and y directions. Now notice this velocity, this net velocity, is moving up and over, which gives it its diagonal direction. So we'd say it's moving in the two-dimensional plane. What that means is that this two-dimensional vector has components in both the y and the x direction. So looking back to our first equation, what it's saying is if we take vx, square it, and add it to vy squared, take the square root of that, we are going to solve for the net velocity. This actually mirrors Pythagorean theorem, which says a squared plus b squared equals c squared. This is because if we square both sides, we're now left with a squared plus b squared, and the square root of that equal to c. So the cool thing about this type of problem is we can treat it like a triangle, because we know it reflects Pythagorean theorem, which is meant for right triangles. That means that if we start with our net velocity, let's say of 5 meters per second, we can actually work backwards and solve for either the x component or the y component. And we can do that by filling in the rest of the triangle. So we vx, and we're going to bring vy over, and now we've created a right angle, and our launch angle will still keep as 30 degrees. Let's say I want to start by finding vy. I can actually think back to our handy trig and SOHCAHTOA, because I know that the sine of this particular angle is going to be equal to opposite over hypotenuse, vy, over our net acceleration. So now with some simple rearranging, I can find that vy is equal to sine of 30 multiplied by 5, vy is equal to 2.5 meters per second. The same thing can be done with vx, except using cosine. So cosine of 30 degrees is going to be equal to adjacent over hypotenuse, which is vx over our net velocity of 5. We rearrange cosine of 30 times the 5 meters per second, and we get a vx equal to about 4.33 meters per second. So what we've done is essentially come up with a general formula that says if we start out with the net velocity, the two-dimensional vector, we could find the components, because vy is actually just the sine of the launch angle multiplied by the original velocity. Correspondingly, vx is going to be cosine of the launch angle multiplied by the net velocity. So these equations might come up in future lectures, but I thought it would be a good time to introduce them here as well. Okay, let me clear this work, and then we'll talk about the next functions or useful expressions. Okay, so these equations here, vx equals ax plus bx, and vy equals ay plus by, are essentially saying the net velocity in both the x and y direction is the sum of all of the individual velocities in the x and y direction respectively. So it's kind of a mouthful. So let's draw a coordinate system to try to visualize what they mean. So let's say I'm moving at a bunch of different two-dimensional velocities. We said that they're two-dimensional, so they have both y and x components, which I'm drawing in here. And you can solve for these y and x components using the method that we just showed. So now if I want to find my vx, all I have to do is add the x components of all of these vectors, which would be ax, bx, cx, etc., and it can go on forever. So now visually depicting this with tip-to-tail addition with vectors, we could say that the final, or the net, velocity in the x direction is simply the components. The same thing can be done in the y direction with the vertical components, which I will highlight here. Now notice in this particular case that I drew out, these vectors would be negative if we designated anything downward as negative and upward as positive, and then these vectors would be positive because we know vectors contain both a magnitude and direction. Okay, last but not least, we'll go over, just briefly, constant acceleration and the constant velocity equations. I say briefly because notice they actually have the same notation as the equations from the previous discussion sheet, but these are now in respect to the y direction, so everything is flipped vertically instead of horizontally, besides this equation right here. So if things are working now vertically, up to down, if we say we have an object, let's say it's a rocket, just like our rocket experiment problem, and it accelerates upward, we would say that this is our y naught, this is our y, and usually if things are moving upward, we'll designate that as a positive, or in the positive direction, and it's not going to be gravity. Usually it could be fuel that drives something upward, or someone throws it. And if we look at the opposite, or a free fall type of a problem, this is now our y naught, this is our y, and gravity is usually going to be the general acceleration that drives things downward, and we'll designate that as negative in most problems. So that applies here, here, and here. Quickly, delta y we can think of as y minus y naught, which is the same thing as just vertical distance traveled. And constant velocity, this one was actually shown in the previous video, except they included the not symbols for notation. So I encourage you to go back to the, I think it was discussion 2A or B, if you want to review that. So I hope this review of useful expressions was helpful.